All right, so now we're going to look at some problems where we mix our trig functions. Where instead of having the same trig function as inverse trig function, we'll do like cosine of inverse tangent, tangent of inverse sine, where we don't have straightforward cancellation properties to rely on. So let's start with this problem here, cosine of the inverse tangent of -1. So this is a problem where we can just do evaluation again, okay, because the inverse tangent of -1 is something that we can work out. What is that? It's going to be an angle between -π/2 and +π/2, whose tangent is equal to -1. And that angle is -π/4. Okay, so that's when we can work out without a calculator. It's fourth quadrant angle whose tangent is equal to -1. That angle is -π/4. Okay, so this is just the cosine of -π/4, and that's going to be 1/√2, or if you prefer to rationalize denominators, √2/2. Okay, so that's just straightforward evaluation. Evaluate the inverse trig function on the inside, and then evaluate the regular trig function on the outside. Okay, so now let's turn our attention to the second example. Okay, this one's a little more complicated because we can't evaluate that inside. So this is the inverse sine of √3/4. So note this is not √3/2, it's √3/4. Now if we really wanted to, we could maybe work this out using a half angle formula, but then finding the tangent value would be a little challenging. So instead what we want to do is rely on our definitions. Okay, so what is the inverse sine of √3/4? Well, it's an angle. It's an angle theta. Since it's an inverse sine, it's got to be between -π/2 and +π/2. And its sine value has to be √3/4. And what we're trying to find is the tangent of that angle. Because again, the inverse sine of √3/4 is just an angle. Its sine is √3/4. We want to find its tangent. This actually comes back to a problem that we've done many times in the past, particularly in Unit 1, where we have a quadrant and one trig function for our angle, and we want to find another trig function value. Okay, so note that since the sine of theta is √3/4, it's a positive sine value. That tells us that theta has to be in the first quadrant. Can't be in the fourth quadrant because its sine value would be negative. Here the sine value is positive. Okay, so theta actually has to be between 0 and π/2 since that sine value is positive. Since we know the sine of theta, we can draw a right triangle with opposite side √3, hypotenuse 4, and then our adjacent side, by the Pythagorean theorem, is the √13. And now what we're trying to find is the tangent of that angle. Okay, but we have all three sides of our right triangle labeled, so the tangent would be √3 over the √13. Okay, or if we want to rationalize our denominators, that would be 13 √3 over, or sorry, 13 √3 over 13. So √39 over 13. We would multiply the top and bottom by the √13. So this sort of solution is something we're going to see a little bit more of moving forward, where if we have the inverse trig function on the inside, we can actually just draw a right triangle because, if we have that trig value, in this case we have the sine value of our angle theta, since theta is the inverse sine of √3/4, we know that theta has to have a sine of square root of 3 over 4, and then we can draw a right triangle in the appropriate quadrant, label 2 of the sides with that trig value, and then find the trig value we're looking for, in this case the tangent, by locating the third side with the Pythagorean theorem. Okay, so we will do, as I said, some similar examples to that in just a moment. Before we do so, I just want to do one example where we have the regular trig function on the inside. These are a little bit more limited because, with one or two exceptions where you can kind of fiddle around with cofunction identities, generally you need the inside to be something you can evaluate. So we can't get too creative with what's on the inside, since it has to be a trig function we can evaluate without use of a calculator. You will see, on some of the ALEKS problems, there will be some with maybe some kind of funky angles where you do have to use a calculator, but if you can avoid using a calculator if your angles are nice, I recommend you do so. Okay, so let's take a look at the inverse cosine of the sine of 5 pi over 4. Okay, so now, as I said, we have the regular trig function on the inside, the inverse trig function on the outside, and this one we can do using evaluation. Okay, because the sine of 5 pi over 4 is something we can work out. 5 pi over 4 is pi plus pi over 4. And so it's going to be a third quadrant angle, so it's going to have a negative sine value. And the sine of 5 pi over 4 is negative 1 over square root of 2, or if you prefer rationalizing denominators, negative square root of 2 over 2. Okay, so now we're just evaluating the inverse cosine of negative 1 over square root of 2. So this is going to be some angle between 0 and pi, whose cosine is negative 1 over square root of 2. So that puts us in the second quadrant between pi over 2 and pi, and the reference angle has to be pi over 4. And therefore, the inverse cosine of negative 1 over square root of 2 is 3 pi over 4. Okay, so we get that the inverse cosine of the sine of 5 pi over 4 is 3 pi over 4. And this is one that we could actually solve by doing a cofunction identity as well. We could replace the sine with a cosine using an appropriate cofunction identity, and then this would go back to the sort of problem that we did in the previous video. Okay, so to finish this video up, I'd like to do some problems where we can take trig functions and actually turn them into algebraic expressions. And this is a skill that those of you who are going on to Math 140 and Math 141 are going to need, particularly when you start doing trigonometric substitution for evaluating various integrals. This is something that comes up from time to time. So what we're going to do is look at expressions where we have a trig function on the outside, an inverse trig function on the inside, and inside that inverse trig function, we're going to have some variable, or some expression involving a variable. Okay, so in this case, we're going to take the tangent of the inverse cosine of 2u. Okay, and we're going to assume here that u, and therefore 2u, is something that's positive. The idea is we're going to do this trick like we had 2 examples ago where I drew the right triangle, and the right triangles we're going to draw are always going to be in the first quadrant. Okay, so to evaluate this, we want to think, what is the inverse cosine of 2u? Okay, well, it's going to be some angle theta. And as I mentioned, for these sorts of problems, we're always going to assume that the angle in question is in the first quadrant to make things easy for us. And the cosine of that angle is 2u, which is the same thing as 2u over 1. And what we're trying to find is the tangent of that angle. Okay, because again, theta is what we're calling the inverse cosine of 2u. We want to find the tangent of the inverse cosine of 2u, or the tangent of theta. Okay, so what we can do is draw our first quadrant right triangle. We make theta one of the acute angles. If the cosine of theta is 2u, can label the adjacent side by 2u, the hypotenuse by 1, so that the cosine is 2u divided by 1. We want to find the tangent of that angle, so we have to find our opposite side. But by the Pythagorean theorem, that's going to be the square root of 1 minus 4u squared, since 4u squared plus this side squared has to equal 1. Okay, and therefore the tangent of theta is our opposite side, square root of 1 minus 4u squared, over the adjacent side, 2u. Okay, so that is really very similar to the problem when I did the tangent of the inverse sine of square root of 3 over 4. The only difference is, instead of our sides all being labeled with numbers, some of our sides are going to be labeled with variable expressions. But we use the Pythagorean theorem to find missing sides, and then we just take the appropriate ratio to get, in this case, the tangent. Okay, so these problems are really pretty straightforward once you get some familiarity with them. They all kind of proceed the same way. The inside expression tells you what sides to label. In this case, since it's a cosine, we have the adjacent and the hypotenuse. And then we use the Pythagorean theorem to find the third side. And then we use the appropriate definition of the trig function to find the outside. In this case, tangent is opposite over adjacent. Okay, so let's do one last example here. This is example 5. Find the cosine of the inverse sine of 3 over u. Okay, same sort of idea, where the inverse sine of 3 over u is going to be some angle theta. I'm going to assume that this is a first quadrant angle, and then by definition, the sine of that angle is 3 divided by u. And we want to find the cosine of theta. Again, we'll draw our right triangle. If the sine is 3 over u, you can label the opposite side by 3, hypotenuse by u, so that the sine is 3 divided by u. We want to find the cosine, which means we have to find the adjacent side. By the Pythagorean theorem, that's going to be the square root of u squared minus 9. Okay, because this squared plus 3 squared equals u squared. Okay, so we want to find the cosine of theta. So that's going to be our adjacent side, square root of u squared minus 9 over our hypotenuse u. Okay, so as I said, once you get the hang of this sort of problem, they really all kind of proceed in the same way. And if you understand how to do these problems, that will really help with your ability to do problems like the first two examples, where we have just numbers instead of variable expressions. The only difference with that is if you draw the right triangle is not necessarily going to be in the first quadrant, because the numbers that we would have if we don't have variables and just numbers might be positive, in which case we would be in the first quadrant, or they might be negative, in which case we would want to be in the fourth quadrant in the case of inverse sine or inverse tangent, or second quadrant in the case of inverse cosine. Okay, and let's just do an example like that really quick to finish this video up. Okay, so let's suppose we wanted to find the cosine of the inverse sine of negative 4 over 5. Okay, so again, we want to find the cosine of an angle. In this case, our angle is the inverse sine of negative 4/5, and therefore theta has to be between negative pi over 2 and positive pi over 2. And the sine of theta is negative 4/5. Okay, so that puts theta in the fourth quadrant, because the sine value is negative. And the vertical side we'll label by negative 4. The hypotenuse of our right triangle we'll label by 5, so that the sine is negative 4 over 5. And then by the Pythagorean theorem, or our Pythagorean triples, the horizontal side is going to be 3. Okay, so this would be our fourth quadrant right triangle. Again, we know we're in the fourth quadrant because this is an inverse sine, which puts us in the fourth or first quadrant. The fact that the sine value of our angle is negative tells us we're in the fourth quadrant and not the first. Okay, so now we want to find the cosine of this angle, and that's going to be 3 over 5. Okay, so very similar sort of problem, but just note, as I said, if there's a negative number inside the inverse trig function, then your right triangle is not going to be in the first quadrant. It will be in the fourth quadrant in the case of an inverse sine or an inverse tangent, or in the second quadrant in the case of an inverse cosine.